Hi, this is Pradeep and welcome to Code Very Prime. In this video lesson, we'll learn about doing heap sort on a given array. This is the first part of the two-part series, and in this video, I will be showing how to build the max heap from the given array. Because until and unless you build the max heap from the given array, you won't be able to perform the heap sort. Now let's suppose that this is the example in which we have been given an array. Now, since this sorting requires a building up of a max heap, and the max heap of this array is this, and since this is a max heap, and you know that a max heap can actually be represented as an array, so its corresponding max heap array is this. And in this tutorial, we will be basically learning how to do this. If you see the array, and the first element that is in the 0th index, 0 is present. So this has been done intentionally so that the calculation of building the binary heap becomes easy. Now remember that for a particular index I, its corresponding left child is 2i and its corresponding right child is 2i plus 1. If you see the first index, which contains the element 8, its left child is present at index 2i, that's 2, and its right child is present at index 2i plus 1, that is 3. Similarly, for index 2, its left child is 2 into 2, that is 4, and its right child is present at index 2 into 2 plus 1, that is 5. Similarly, you can also match up the other indexes also. Now we're going to see how to do this from the scratch. And also remember that since this is a binary max heap, therefore the root will be greater than its corresponding left and right child. And also the tree will be a complete binary tree. Now in the given array, we'll move from left to right. The first element in the counter is 6, and then we'll append that inside the heap array. If we put this element as the root of the binary heap, then 6 is gonna come at the top. The next element is 5. So again, we put it in the heap array, and remember that for a particular index I, its left child is 2i. So for index 1, its left child is 2. Therefore, in the heap tree, at the left of 6, 5 will come in. We're gonna move further right, append this element inside the heap array, and now we see that the index 3 is actually the right child of index 1. So 3 comes at the right of 6 in the heap 3. The next is 1. Append it inside the heap array. Index 4 is the left child of index 2. So 1 will actually come at the left of 5 in the heap 3. The next is 8. Append it inside the array. And you can see that index 5 is actually the right child of index 2. So 8 is going to come at the right of 5 in the heap 3. But as soon as this happens, it violates the property of the max heap tree. That is, the property says that the root should be greater than its corresponding left and right child. But here in the heap tree, you can see that the root is 5 and its right child is 8, and 8 is greater than 5. So it surely violates the property. Therefore, we'll have to restore the property of this max heap. Therefore, we're going to bubble up 8 in the place of 5, and 5 is going to come at the place of 8. And since we have made this change in the binary tree, so it's going to reflect the heap array also. When 8 comes at index 2, you see that it has yet not restored its property. That is, for see at this place, then the root is actually lesser than 8. So again, we will have to bubble it up. 8 will come at the position 6, and 6 will come at the position of 8. So we now see that the heap property is restored. So now the next element that we encounter is 7. So we'll push the 7 inside the heap array, and we see that 7 comes at index 6, and index 6 is actually the left child of index 3. So inside the heap 3, 7 will come at the left of 3. So now when this happens, again you can see that it has violated the property of max heap. That is where you can see that 3 is actually less than 7, which should not have been the case. The root should be always greater than its corresponding left and right child. So again, it will bubble up, that is 7 will come in the place of 3 and 3 will come down at the place of 7. And after doing this, it sees that it has restored its max heap property. So now we're going to move ahead, and now we're going to come at this position. So we're going to append 2 inside the heap array, and we see that 2 comes at index 7. And index 7 is actually the right child of index 3. Therefore, 2 is going to come at the right of 7 in the binary heap. You see that the property is not violated, so we're going to move ahead without making any change. Now in count of 4, we push that inside the heap array and also in its corresponding position in the heap 3. Upon doing this, we see that it has violated the heap max heap property. So here 4 is actually greater than the root, and actually the case should have been that the root should have been greater than its left child. So again 4 will bubble up at the position of 1 and 1 will come down at the position of 4. So now we see that the max heap property has again been restored. So this is how it is done, and now we're going to see how to code this thing out. So I'm going to first build a class heap, and this class heap I'm going to define a constructor, so that whenever we're going to make an object of the class heap, this constructor will be called by default and a list will be made by default, and the first element of the list will be 0 and the current size will be set as 0. This list L is actually the heap array, and the first element is set as 0 in this heap array. The current size is 0, and this element 0 is actually not considered as a part of this heap array. This 0 is included just to make calculations a bit easier. That is, this inclusion of the 0 makes the left child of a particular index I as 2i and the right child of a particular index I as 2i plus 1. And as we're going to append element of the given user array inside this heap array, we're going to increase the current size by 1, and the value of the current size is actually going to denote the last index of the heap array, and the element present at the current size index, if it's greater than that its root, then we're going to have to do a swap. So now let's suppose that the array that has been given to us is this, and we have to do heap sort of this array. Now I'm going to define a function called insert, and this insert function will be responsible for inserting element 1 by 1 from this array into our list array, that is L, and this L basically denotes the heap array. So now we're going to crawl over the array, and then we're going to append 1 by 1 inside the list L, which is our heap array. After this, we have to increase the current size by 1, and remember that we can access L and current size by using self, because L and current size has been defined inside the constructor of the class heap, and we're going to access L and current size by making an object of the class heap, and we're going to say self.L and self.current size. That is saying that L and current size can be accessed by making use of the object, and here self basically denotes the object. Now after appending the array element inside the list, we will have to check whether it has violated the max heap property or not. That is, if the element is actually greater than the array, then we will have to swap. So for that, we're going to make use of another function that I'm going to define later, and I am going to pass the index of the current position inside this move up function. So this is the mover function which will be responsible for checking whether it has violated the max heap condition, and if it has violated the max heap condition, then it's gonna swap. So it's gonna swap the index this with its root. So this index, that is the current size, is actually the index at which the last element of the heap array is located at. So initially current size was 0, and as we append elements from the array inside this list L, our current size is gonna increase by 1. And so on. And every time we append an element from the array inside this list L, we're going to check the property of the max heap, and our mover function is going to take care of it. So this current size value refers to the last position inside this max heap array. So when current size is equal to 4, the last position means that it is at the index 4 of this max heap array, and we're gonna pass this index 4 as a parameter to the move up function. So now we're going to define a move up function which will be responsible for swapping the last index value of this heap array with its root. So this is a move function, and it's gonna take parameter as index, and this index is actually whatever we pass here, that is the last index of the heap array. So this move up function will swap every time it finds that the last index is greater than its root. So for making that comparison, I'm going to actually define another function called compare with root, and it's going to take the same index as that of the move up function. Inside this compare with root function, first it's going to calculate the root of the index, that is index /2. So / denotes that it's going to compute the absolute value of this division. For example, 4 divided by 2, it gives 2, and 5 divided by 2, it should have given 2.5, but since this is an absolute division, so it will be 2. So 5 divided by 2 will be 2, and 4 divided by 2 will also be 2. Therefore, for index 4, its root will be 2, and for index 5, its root will be again 2. So now, after calculating the root index, after doing the absolute division of the index, so now we're going to have to check if the value at index is actually greater than that of the value of the root. If it is so, then this is going to return true, or else it's going to return false. Now inside our move up function, we'll be making use of this compare with root function. Then we're going to perform a swap. So when we are at this position, when 8 comes at the index 5, so definitely it violates the property of the max heap. So we're gonna have to do the swap operation here. And after doing the swap operation, it again fails to restore the property of the max heap. Therefore, again, it has to do a swap. Therefore, in my code, I'm going to define a while condition, that is while 1. I'm going to first check if the self.compare with root returns a value of true. If it returns a value of true, then do a swapping, and after the swapping has been performed, simply change the index with that of the root, which means after doing the swapping, the next time this while function runs, it will pass this index inside this compare with root function. So this newly changed index is that of the root. So in our example, the first time this while loop ran, the self.compare with root function had the index of 5. It returns true, so therefore the function move up function did swapping, and after doing swapping, our index was changed to that of the root. So the root was the index 2, so now the index has become 2. So now when the index has become 2 and the while loop reruns, it passes the index 2 as the parameter to the compare with root function. Now again, the compare with root function returns true because the element at index 2 is actually greater than its root. So again, when it has returned true, again it will do swapping, and after doing the swapping, 8 has finally come at index 1. So now we will have to swap, we'll have to stop, because there can be no more comparison, because index 1 is the ultimate root of the entire binary heap tree. So inside this mover function, I'm going to say if index is 1, simply break the entire while loop. And even though the index has not finally become 1, and in between the max heap property gets restored, so even then simply break the while loop, because it's not necessary that every time index will change and it will finally become 1. So there can be possibility that even by doing one swapping, the max heap property has been restored. So when the max heap property has been restored, so the self.compare with the root function is going to return false, and when that happens, it will simply break the while loop, saying that the property has been restored. And since this swapping requires the use of this root, so we will have to define this root here also. So root is index /2. This defines the floor division or the absolute value of the division. And also see that I have made the object of the class heap, and I have called the insert function by making use of the object. So when I run this program, we see that the resultant heap array that we got is 8674531, and we have also printed the list that we finally made, that is the heap array. So this is the heap array that we were supposed to get, and this is absolutely correct, which means our program is absolutely correct. So this is the way we actually made the max heap, and after building this max heap, we'll be actually doing the heap sort. So that is for the next lesson. Until then, goodbye. Like and share this video, and thanks for watching.